Hello to everyone. Welcome to the course on numerical linear algebra and application. Today we are going to learn 11th module 4th lecture, that is 54th lecture of this course. As we have seen in the previous 3-4 lectures, how the system of equations Ax is equal to b can be solved by using iterative procedures. We have also seen well-known procedures: Gauss-Jacobi method, Gauss-Seidel iteration method, successive or relaxation method, Cholesky decomposition, singular value decomposition, power method, and many more. Today we are going to see some new concepts, some extension to what we have done for the Jacobi iteration method. Basically, it's a kind of recalling what we have done in the previous lecture so that you get familiarity with the Jacobi iteration method. Jacobi iteration method consists of diagonalizing a matrix A by applying a series of orthogonal transformations, that is B1, B2, B3, Br, so that their product T satisfies the equation B1 transpose A times of B1 will be equivalent to a diagonal matrix D. Their product T satisfies the equation B1 transpose A times of B1 will be equivalent to D, where D is a diagonal matrix. To reduce the matrix A to a diagonal matrix easily, we choose the largest non-diagonal element from A and form a 2 by 2 submatrix. So A1 is equal to AII, AIJ, AJI, AJJ, where AJI is same as AIJ. Consider the orthogonal matrix B1, cos theta minus sin theta, sin theta cos theta. Then we will have the matrix B1 transpose A1 B1, which will be equivalent to cos theta sin theta minus sin theta cos theta, and A1 will be AII, AIJ, AJI, AJJ multiplied with B1, that is cos theta minus sin theta cos theta. So which would be equivalent to AII cos square theta plus AJJ sin square theta plus AIJ sin 2 theta. And second element is AIJ cos 2 theta plus 1 by 2 times of AIJ minus AII sin 2 theta, and the last row will be AIJ cos 2 theta plus 1 by 2 times of AIJ minus AII sin 2 theta, and last entry would be AII sin square theta, AJJ cos square theta minus AIJ sin 2 theta. Now the matrix will reduce to the diagonal form Aij cos 2 theta plus 1 by 2 times of Aji minus Aii times of sin 2 theta is 0. Then you will have, if sin 2 theta happens to be, that is tan of 2 theta happens to be 2 times of Aij upon Aii minus Ajj. The equation 2 gives the 4 values of theta, but for the least possible rotation we choose minus pi upon 4 less than or equal to theta less than or equal to pi by 4. So the values of theta lies from minus pi by 4 to pi by 4. So with the values of tan d theta is 2aj upon aii minus ajj. Thus, the equation 1 which we have noted down, that is the 2 by 2 matrix equation, reduces to diagonal matrix, and we can find a new matrix A2. As a next step, we choose the largest non-diagonal element from the rotated matrix A2, and using the orthogonal matrix B2, we repeat the above process. In this way, a series of such transformations are performed. After making all transformations, we obtain a matrix BR1, BR minus 1, 1, BR minus 2, 2, B1 minus 1 multiplied with A multiplied with B1, B2, B3, Br minus 1, Br, which will be equivalent to B minus 1 AB. As R approaches to infinity, B inverse AB approaches a diagonal matrix whose diagonal independents are the eigenvalues of the matrix A. Also, the corresponding columns of B, that is B is equal to B1, B2, Br, are the eigenvectors of matrix A. So, we will have some very simple example. This example is, look at this example. Apply Jacobi process to evaluate the eigenvalues and eigenvectors of the matrices. That is, the one is 5, 0, 1, 0, minus 2, 0, 1, 0, 5. This is a 3 by 3 matrix. And second one is 4, 1, 1, 1, 1, 2, 1, 2, 1. This is again another 3 by 3 matrix. Here the largest non-diagonal element, that is A13 is equal to A31 is equal to 1. Also A11 is equal to 5, A33 is equal to 5. And tan 2 theta is 2 into A13, 2 into 2, 5. So this is anyway 0, so this goes to infinity. So that means 2 theta is equal to tan inverse of infinity, which we know very well it is pi by 2. So obviously theta will be pi by 2 times of 1 over 2, which happens to be pi by 4. Then B1 is equal to cos theta 0 minus sin theta, 0, 1, 0, and this is sin theta, 0, cos theta. So, which will happen to be 1 over root 2, 0, minus 1 over root 2, 0, 1, 0, 1 over root 2, 0, 1 over root 2. The first transformation gives D1 is equal to B1 inverse A1 B1. So that will be equivalent to 1 over root 2, 0, 1 over root 2, 0, 1, 0, minus 1 over root 2, 0, 1 over root 2. Multiplied with A1. So this is the A1 and B1 is this matrix. So when you multiply these two matrices along with A1, that is D1 is equal to B1 inverse A1 B1. So essentially it turns out to be matrix of this form. So you see here, this is the main diagonal. So essentially lambda 1 is equal to 6, lambda 2 is equal to minus 2 and lambda 3 is equal to 4. Here the eigenvalues of the given matrix are 6 to minus 4 as we see from this representation. And the corresponding eigenvectors. So for each eigenvalue you find out and the corresponding eigenvectors are the columns of this matrix. You see here the first entry A11 is 1 over root 2, A12 is 0, A13 is minus 1 over root 2, A21 is 0, A22 is 0, sorry it is 1, A23 is 0. Similarly A31 is 1 over root 2, A32 is 0, A33 is 1 over root 2. The eigenvalues are lambda 1 is 6, lambda 2 is minus 2, lambda 3 is 4 and corresponding eigenvectors are, these are the eigenvectors. So x1 is equal to 1 over root 2, 0, 1 over root 2 and x2 is equal to 0, 1, 0 and x3 is equal to minus 1 over root 2, 0, 1 over root 2. Here you see again the largest non-diagonal element is A23 is 2 and A22 is 1 and A33 is new element. So you will write it as is infinity, so theta is equal to pi by 4 again here. So you will have B1, therefore you will have 1, 0, 0, 0 cos pi by 4 minus sin pi by 4, 0 sin pi by 4 cos pi by 4. So which turns out to be anyway this is 1, 0, 0 cos pi by 4 cos 45, it is 0.707 and this is same as sin 45. So that is actually 1 over root 2. So that is 1.0000 upon 1.414 which turns out to be 0.707. This is okay, this is fine. The first transformation gives you D1 is equal to, that is B1 inverse times of A1 B1. So you will have B1 inverse is this matrix and A1 is this matrix. This is the matrix A1 and this is the matrix B1. You will have again B1, that is 1, 0, 0, 0.0, 707 minus of 0.707 0 0.707 0.707. So ultimately when you multiply these three matrices, you end up with this matrix, that is 4.0, 1.41, 0, 1.41, 2.99, 0, 0, 0, minus 0.99, which we call it as A2. Here in the matrix A2, the largest non-diagonal element is, that is A12 is equal to A21 is equal to 1.41. Also we see A11 is 4, A22 is 3. So we can write this tan theta the way which we did it earlier. So tan of 2 theta is nothing but 2 into A12 upon A11 minus A22. So which turns out to be 2.82 as calculated. So that is tan of 2 theta. So which implies theta will be equivalent to this value 35.23 degrees. So this is the second transformation, D2 is equal to B2 inverse A to B2. So when you do this, this D2 is nothing but, and this is the value, and this is the second value 0, fine, and multiplied with these values. So you get the matrix multiplication, this matrix, right? So when you multiply this, that is the way which we did it, this is B2 inverse, and this is A2, and this is B2. So which you ultimately you arrive this matrix of this form. So when you approximate this, so you get a matrix of this form. This is the form which you get it. So this is the main diagonal, and this is the leading diagonal, and this is also diagonal. So you will have only main diagonal are non-zeros, rest are all zeros. So you can write this eigenvalues, lambda 1 is equal to 5.0, lambda 2 is equal to 2.0, lambda 3 is equal to minus of 1.0. The corresponding eigenvectors are the columns of B, that is B1, B2. So the matrix is, this is the B1 matrix, and this is the matrix B2 matrix. So as we see this matrix, when you multiply this matrix B1 and B2, you could able to arrive to this matrix B, that is 0.817 minus of 0.577, 0, 0.408, 0.577, this thing. The eigenvalues are, you will have lambda 1 is equal to 5.0, and lambda 2 is equal to 2, lambda 3 is equal to minus of 1.0. So corresponding to each eigenvector, you will write Ax is equal to lambda x, or else A minus 5 multiplied with x is equal to 0. So corresponding to that, you get this eigenvector when you solve it. Similarly, that is A minus 2 of x is equal to 0, you get this vector. Similarly, A minus A plus 1.0 of x is equal to 0, so you get this vector. So therefore, three eigenvectors are being obtained. So in the similar fashion, we will have a few more examples on householder and other methods. Reduce the following matrix by householder method. See, you are given 1, 2, 3, 4. So it is a 4 by 4 matrix. Right? I want to find out the reduce this matrix by householder method. So here I will take as per the algorithm W1 of transpose is nothing but 0, W2, W3, W of 4. 0, W2, W3 and W4. And P1 is equal to, that is I minus 2 W1, W1 transpose, you get a matrix of this form. So that is I minus 2 times of 0, W2, W3, W4 multiplied with 0, W2, W3, W4. So you get a matrix of this form. So you get 1 minus 2 W2 square minus 2 W2 W3, that is 1 minus 2 W2 W4 square. So this form you get it when you simplify this. So let us take that S is equal to, let's say, A12. You get a matrix of this form, that is 75 square plus 100 square whole power 1 by 2. So ultimately we will end up with 125. Now from the formula we have W2 square is 1 by 2 times of 1 plus or minus A12 by S. So ultimately we will end up with the value called 4 by 5. Similarly, when you do W3, you ultimately end up with a value called 1 over square root of 5. So W4 happens to be 0. So you get a matrix P, that is 1, 0, 0, 0, 0 minus 3 by 5 minus 4 by 5, 0, 0 minus 4 by 5, 3 by 5, 0, 0, 0, 0, 1. So you get a matrix of this form, that is P1 transpose P1 is equal to, which implies P1 times of A1 P1 transpose P1 A1 P1, and ultimately you get a matrix of this form, that is 100 minus 125 0 0 minus 125 59 12 0 0 12 66 55 0 0 55 25, which is a reduced triangular matrix. You see here, this is the main diagonal, this is the sub diagonal, this is a super diagonal. So rest are all zeros. So therefore it matches very well with the one which we wanted to have, tri-diagonal form. So in the similar sense, we can do some more examples, especially when the matrices are in special shape. That is, for example, if it is diagonally dominant, what would happen? Look at this 3 equations, 3 unknowns. You will have 3 equations, 3 unknowns. Check if the diagonal entries are, see that 3 is greater than 2 plus or absolute value of 1, which is correct. 3 is greater than 2 plus 1, which is correct. 4 is greater than 1 plus 2. So if you check it arbitrarily, so this will satisfy diagonal dominance. Diagonal dominance. So the first approximation is, as you know very well, that is 3x1 is equal to 4. So x1 you get it as 1.33. 3x2 is equal to 5. x2 you get as 1.67. 4x3 is equal to 7. You get x3 is 4.25. So essentially x1, x2, x3 you get it as, that is 1.33, 1.67, 4.25. Calculation of the residues you do from the first equation R1, you will have 3 into 1.3, so you ultimately end up with minus of 0.92. Second equation if you do, you end up with minus of 1.58. Third equation if you do, you end up with 4.67. So similarly, when you do the second iteration, you will have AIIX1 is BI minus R1, so which you end up with x1 is equal to 1.64. So the increment is minus of Ri of 1 upon AII, so which is essentially 0.3067. Similarly, when you do AIIXI, which is x2 turns out to be 2.1967. So the increment is 0.53. Similarly, AII, so when you do, the x3 turns out to be 3.0825. So the increment here is 1.1675. The process is repeated with row values of x1, x2, x3 and the revised residual Ri2 and the corresponding increments are determined. So you will be able to find out from the the residue calculation. From first equation we have Ri of 2 is, this equation you do get 2.2309. From second equation you do get 1.7876. From third equation you get 1.363. So 3 you do get in these equations. So third approximation when you do it, that is AIIXI is BI minus Ri2, so which you get as this matrix, that is 0.5897. And increment when you do it, so ultimately it is minus of 0.5959. So you end up with a constants and residue if you do that, that is AII and BII, RI1, RI2, RI3. So you get 3, 4, 3, 3, 4, 4, 5, 17, and you get RI1, RI2, RI3 as computed over this table. So similarly, so essentially we wanted to find out the unknowns, that is x1 is in the first iteration, you know, it is very trivial, basic values, what is being given. Second iteration, there is an improvement over here, first increment, and if you do second increment, this is the value, third increment is, these are the values, final values. So if you look at 1, 2, 3, from the set of equations, look at here. So 3 into 1 plus 2 into 2 minus 3. So 3 plus 4 minus 3, which is 4, fine. Second equation is 2 into 1 minus 3 into 2 minus 3. So 2 minus 6 minus 3. 2 into 1 plus 3 into 2, 6 minus 3. 6 to 8, 8 minus 3, 5. Fine, that is fine. Third equation, 1 into 1, 1 plus 2 into 2, 2 plus 4 into 3. So 1 plus 4 plus 12, 17. It is fine. So it is satisfied. So the first approximation holds, second approximation also holds, third approximation also holds. So therefore it satisfies this value. Now let us look at into another set of equations, right? So these are the dominant values. 100 is greater than this, 130 is greater than this. So this is also diagonally dominant. This is also diagonally dominant. So when you write it, the calculation of residues, first equation, you do get this value, and when you do this second value, you do get like this. And from the second approximation, that is AIIXI will be equivalent to BI minus RI of 1. So you end up with this value. Third increment, when you do it, you end up with this value. So the way which we did it in the previous case, same thing can be computed over here. See that increment over here, minus Ri of 1 upon AII, which is equal to minus of 2.2395, and second increment is 0.0811. The process is repeated with new values x1, x2, x3 and revised residuals Ri2, and the corresponding increments are determined. The process is repeated till satisfactory results are being obtained. So the calculation of residues, if you do first equation, you do get minus of 1.5148. From second equation, you do get 0.7228. Similarly, from third equation, you do get minus of 0.6176. So the third approximation will be given by Bi minus Ri of 2. So essentially, you will end up with this matrix. That is, x of 1 is equal to 3.935 of 1. And the increment will be like this. So you get this value. Second increment, you get this value. Third increment, you get this value. So these are the values which you do obtain while doing this process of calculation. So the increment will be minus of Ri of 2e upon AII. Since you know EI is not equal to 0. So therefore you get the value 0.0094. So ultimately when you tabular this, so the values of AII, BII, RI1, RI2, you get like this. So the computation becomes very easy and it is pretty good from this table as we see here. Similarly, you can see over here the how x1, x2, x3 and these are all basic values as you know very well. And when you do the first increment, that is Ri of 1 upon AII, so you get these are the values. Similarly, when you do the second increment, you got the values. Third increment, when you do, these are the values you get it. So essentially it is 4, 1, 2. These are the values. So one could verify from the previous example 4, 1, 2. So you see here 4, 1, 2 when you do it, 4, 1, 2 when you do it, 4, 1, 2. So you can find out from this example, yes. So 100 into 4 plus 4 into 1 minus 6 into 3. So 404 minus 18. So this is 392. Okay. So like that you can compute all the unknowns. So today what we learned is, we have learned 2-3 examples how the Gauss-Jacobi method and how the Koleski decomposition can be used with the incremental values, how it converges, gets accelerated to get the best approximate numerical solution. So thank you very much for listening to my lecture today. Thank you once again.